BMS group already at spatial infinity, and in fact show that it's the same BMS group as the one at null infinity, which also shows that the BMS symmetry is really a symmetry of the theory and not just a symmetry which you see, which exists at null infinity. It's a full theory, a symmetry of the theory. Now, another reason for studying the behavior of the BMS group and how the BMS group acts at spatial infinity is given by the following consideration. Now, if you have followed the recent developments in the study of the asymptotic structure of gravity at null infinity, you know that there are so-called matching conditions of the field that you impose between the past of future null infinity and the future of past null infinity. So there are matching conditions which were explicitly proposed by Strominger, which relate the field here and the field there. However, going from the past of future null infinity to the future of past null infinity clearly involves going through spatial infinity. So really, if you want to understand the matching from a deeper point of view, it's important to understand what happens at spatial infinity. This is, okay. Now, actually, it's a non-trivial question. And actually, that it was non-trivial was well known to mathematical relativists since a long time. And it's a non-trivial question because of the following reason. If you might ask the question, suppose I'm giving you reasonable initial data. Is it clear that they will lead to a null infinity with all the smoothness properties that people usually assume about null infinity? In fact, the existence of null infinity, you can argue, is a dynamical question. And so really you should see whether a null infinity with all the smoothness properties that are usually assumed indeed would exist for reasonable, physically reasonable. Of course, you have to define by what you mean by physically reasonable Cauchy data. And this has been studied by mathematical relativists, so Friedrich being perhaps the one who have contributed deeper insight. And they showed that in general, if you take Cauchy data, which are reasonable in the sense that the energy is finite, they have all sorts of nice properties. Nevertheless, when you evolve the metric from to see how it behaves at null infinity, so you have to integrate the equations of motion asymptotically, you find that it will develop logarithmic divergences which are dominant with respect to the expected and generally assumed behavior of the metric and, in fact, even the Weil tensor. So it's completely in the diffeomorphism invariant statement as you go to null infinity. And if you get some singularities at null infinity, the matching conditions are a bit tricky to analyze. So this is, I will come back, I will say a few more words about that later when we do the construction of the symmetry at spatial infinity. And then perhaps the final reason is as you go up in dimensions, the definition of null infinity is more complicated. Now, in even dimensions, there have been proposals, but in odd dimensions, so in particular in 5 dimensions, which is just the dimension above 4, if you look at the definition of null infinity, people have realized that the gravitational field will decay at null infinity with fractional powers of 1/r. And because of these fractional powers, again, smoothness properties are not so obvious, and what to impose is not clear. However, there exist soft theorems which have been related to the BMS group, to the BMS symmetry, and so you might ask the question of which symmetries are these awarded entities, which is a work that has been done in 4 dimensions. And the answer is somewhat not immediate, that I should say, at null infinity. Probably we can reanalyze it in the light of what has been done at spatial infinity, because by contrast, at spatial infinity, there is no conceptual problem in uncovering the infinite dimensional symmetry that contains a Poincaré symmetry at spatial infinity. So the analysis performed in 4 dimensions can be straightforwardly, conceptually at least, it's technically more complicated, and gravity being a nonlinear theory, I mean, it's indeed rather involved, but conceptually at least there is no problem in extending the analysis from 4 to 5 dimensions, and this problem of fractional powers, it does not get into the way as you go to spatial infinity. And so you can exhibit an infinite dimensional BMS5 group at spatial infinity, and you can, and it's interesting also because canonically you can show that you don't get just an ordinary Lie algebra in terms of the Poisson brackets of these of the generators of the BMS5 symmetry, but you get an interesting nonlinear structure, as I will explain later in the talk. So indeed, the purpose of this talk will be to provide the general ideas of this asymptotic analysis at spatial infinity, starting from 4 dimensions and then going on to 5 dimensions to illustrate. And as I said, I will work on space-like hypersurfaces that are asymptotically flat hyperplanes approaching so spatial infinity, and I will use Hamiltonian methods. Now, this is work done with these people. I am not explicitly writing the references, but if you want to get them, just ask me at the end of the lecture. Now I will start with that. I will recall or give the general ideas of what are asymptotic symmetries from the point of view of the Hamiltonian formalism. So I will start actually for that, and then with that, and then I will move on to the asymptotic analysis in 4 dimensions. So a central role in the analysis, as I said, is played by the action. So the gravitational action will be central in my whole analysis. Well, the action is usually central, is always central in physics. And since I'm Hamilton, I will use a Hamiltonian formalism. I will write the action in Hamiltonian form. That has been done by Dirac and ADM. And the action in canonical form takes the standard form PQ dot. So that tells you that pi is a momentum conjugate to g. So this is a standard kinetic form in Hamiltonian form, so PQ dot minus h. Now, because we have a diffeomorphism invariant theory is gravity, h is actually a combination of constraints, which I have written hi and hi graph and h graph. I'm considering pure gravity. And then if there is a boundary, and this is the case here, we are in the asymptotically flat context, there can be a surface term at infinity. And actually, the surface term at infinity is everything. So I will say more about that. Now, the constraints explicitly take the following form. So you see that the dimension dependence occurs only in the, in the so-called super Hamiltonian, so the Hamiltonian constraint. And it occurs here. So D being the space dimension. Okay, so here is the Hamiltonian. So this completely defines well the dynamics, except that you have to be slightly more precise if there is a boundary, because you have to supplement. You have to tell how the fields behave at infinity. You have to completely define phase space. So phase space is the space of the pi's ij's, which are conjugate to the gij and the dij's. But you have to tell how they behave at infinity, and then you have a complete definition of phase space. And I will insist that the boundary conditions at infinity make this action finite. I want the action to be finite, and finite on the nose, and not just finite after regularization that might be coordinate dependent and so on. If I can have the action finite, why not? Okay, and I can. So I will devise boundary conditions so that at no stage I have infinity. In this classical analysis, I have infinities. Okay, now what is a symmetry? A symmetry transformation will be a phase space transformation. So that will be a transformation mapping the fields gij. So this depends on x spatial coordinates. I'm not writing it explicitly, but these are really d-dimensional fields. So it will be a transformation that map these a set of a configuration of gij and pij to another one, which of course should preserve the boundary conditions. You don't want to get out of the defined phase space. and also should leave the action invariant up to surface integrals perhaps at the time boundaries. Now, why I insist on that the surface integral should be only at the time boundaries? Because I want to have a canonical transformation, and I want the symplectic 2 form, which I can read from the action. So the action was just the standard PQ dot at the standard PQ dot term. So the symplectic would be D form, would be the 2 form, dPij, dJij. I have put a vertical here. Well, you can, it's not really, it's just to record that this is the exterior derivative in phase space, not the exterior derivative in space-time, okay? So this is a D in phase space. And so if the action is invariant up to surface integral at time boundaries, the canonical, the symplectic form will be strictly invariant and not invariant up to surface terms at the space boundaries. And because it is strictly invariant, I have a true canonical transformation. And because I have a true canonical transformation, I can define its generator using the standard Hamiltonian techniques. And so there will be a canonical generator, which furthermore will be a constant of the motion. Now, among the symmetry of the action, there will be what we call asymptotic symmetries. Now, asymptotic symmetries, and I will explain why the terminology asymptotic, will be a gauge transformation, so a diffeomorphism in our case, that fulfills the above conditions. So leave the action invariant and preserve the boundary condition, so it's a map of phase space on phase space, and leave the action invariant. And because of that, it will be canonically generated, so one can write its canonical generator, and because it's a diffeomorphism, actually its canonical generator will have a very specific structure. It will be given by a bulk integral, which will be proportional to the constraints, so to the Hamiltonian constraint and the momentum constraint, which are first-class constraints, which means that the bracket of the constraints among themselves vanishes because of the constraints, plus a surface integral at spatial infinity. And actually, that's very important, as we will see. And because when the constraints hold, the only thing that remains from the canonical generator is the surface term at infinity. So from that point of view, the surface term at infinity is everything. Now, in fact, in gravity, we expect all symmetries to be of that type. Now, among the asymptotic symmetries, there will be what we call trivial or proper gauge transformations. And these are the ones which are purely generated by the constraint. So for which the surface term is equal to 0 for all configurations obeying the boundary conditions. Okay? If that is the case, then this will be a proper gauge transformation. But if the surface term does not vanish, then we use the terminology improper gauge symmetry, because it looks like a gauge transformation. I mean, it takes the same form, but because the parameters do not decay at infinity, they will have non-vanishing surface terms. And if the generators, the surface terms occurring in the generators are equal to 0, these are improper gauge, not equal to 0, sorry, don't vanish. They are called improper gauge symmetries. Now, it's very important to make the distinction, because while proper gauge transformations should really be quotient out, I mean, we have to take the quotient by the proper gauge transformations. It's a redundancy in the description of the system. The improper gauge transformations do have a non-trivial action on the physical states. And so in particular, and for that reason, they should not be factored out. So there is a big distinction between the two. Now we can show that the proper gauge symmetries form an ideal, and so it's algebraically consistent to take the quotient by them. And the physical asymptotic symmetry algebra is the quotient of all the gauge transformations, preserving the boundary conditions, so by the ideal of the proper gauge symmetries. So you only focus, what remains are, in a sense, representative in each class of improper gauge symmetries. And and this actually justifies the term an asymptotic symmetry, because you can see that the physical content of an asymptotic symmetry is completely determined by its asymptotic behavior, whether the boundary charge is 0 or not. And two asymptotic symmetries which have the same charge should be identified. So the only interesting physical information about an asymptotic symmetry is how it behaves asymptotically, hence the name. Now, this distinction between proper gauge transformation and improper gauge transformation from the point of view of the Hamiltonian formalism was, I think, given first in that reference. Okay, now the observables, so the physical quantities, are required to be invariant only under proper gauge symmetries. So in our case, the case of gravity, under diffeomorphisms that vanish asymptotically and with 0 charge, to be more precise, but are not required to be invariant under diffeomorphisms that do not vanish at infinity. Okay, so they are not required to be invariant under the asymptotic symmetry algebra, which is this quotient algebra. They might form non-trivial representations. Okay, they are not forced to be in the trivial representation. And a prime example is given by the asymptotic charges themselves. When the asymptotic symmetry algebra is non-abelian, they will transform non-trivially, because you just compute the bracket and you will not get 0. And so they are not to be required to be invariant under the asymptotic symmetry in particular. Now, this is completely sensible on physical grounds, because if you consider, for instance, a moving black hole, it will not have the same charges as a non-moving black or black hole at rest. I mean, for asymptotically initial observers, there is a distinction, and the distinction is made by the value of the asymptotic symmetry generators. Even though the two situations differ by a diffeomorphism, they differ by a diffeomorphism which do not vanish at infinity with a non-trivial action, and that's perfectly okay. Okay, so I will go quickly on that, but let me just stress that because there are observables that transform non-trivially under improper diffeomorphism, clearly they cannot be expressed only in terms of the curvature invariance, because the curvature invariants are invariant under all diffeomorphisms, not just the ones which are proper, but also under the improper one. So a quantity that is not invariant under improper diffeomorphism will also involve quantities that are not expressible in terms of the curvature. Now, one example which is well known is Chern-Simons in 3 dimensions, but let me skip it. So I will go quickly on that. And if you have questions, I can come back to that later. But so that's perfectly okay and well appreciated. So having said these general considerations on asymptotic symmetries and proper and improper gauge transformations, let me come back to, or let me look at the case of 4-dimensional gravity in the asymptotically flat context. Now, in the Hamiltonian formulation, boundary conditions, well, okay, first a general consideration, and then we go to the description. Now, first of all, it's clear that when you give boundary conditions on the metric and its conjugate momenta, because the metric and the conjugate momentum involve are not invariant under diffeomorphism, you are somehow always implicitly making some gauge fixing, because you are expressing the boundary conditions in terms of variables that do transform under gauge transformations. Now, this is all right if the implicit gauge conditions only freeze proper gauge transformations, because this you have the right to freeze. But if they freeze also improper gauge transformations, you are somehow eliminating the possibility of making physical transformations with physical contact. This is questionable. And of course, defining boundary conditions is not always completely straightforward. So the question which is natural is, how do we know that we are not freezing something that we should not freeze? Now, I don't have a general answer to that, so I will, at this point, go to the example of 4-dimensional gravity to illustrate this idea. Okay, now the standard boundary conditions for Einstein gravity in 4 space-time dimensions in the Hamiltonian formalism have been given by Regé and Teitelbaum, and they are as follows. So in asymptotically Cartesian coordinates, you would require, you are in 3 + 1 dimensions, so the metric will deviate from the flat metric by a term that decay as 1 over r, and its conjugate momentum, well, you can check on solutions, will deviate from 0, which is a value for Minkowski, so from the background value. So the background value is here, delta ij, here the background value is 0. So it will deviate from 0 by terms that decay now as 1 over r squared. But as Regé and Teitelbaum showed, in order to have a consistent theory, I mean, action well-defined, surface integrals well-defined, etc., this decay is not sufficient. You have to supplement it by some parity condition on the leading order of the field. So this is only on the leading order. The next order can be of any parity. So these are functions of the angles. So this is a unit normal. So it's a way to write function of the angle, so theta and phi. This is a unit normal to the sphere at infinity. Now, as I said, they involved, this was the proposal by Regé and Teitelbaum, they involve strict parity conditions under this antipodal map on the sphere. And you may then ask, what are the diffeomorphisms that preserve these boundary conditions? This is what we are supposed to ask as a question to determine the asymptotic symmetries. Now, you can find that, and this is not a surprise, these boundary conditions are preserved, including the parity conditions, by the homogeneous Lorentz transformations, boost and spatial rotations, which have also a definite parity, so that's why they are preserved. Then they are also preserved by translations, where A0, so these are time translations, orthogonal to the Cauchy hypersurfaces. These are tangent translations, so these are space translations. So these are constants, so these are standard translations. But then you have also some sort of super translations, and where these functions, so you would make a translation in time that could depend on the angle. So it would be of order 1 like the ordinary translation, but it would depend on the angle. And you could also make a translation in space that could depend on the angle. But because you have to preserve the parity conditions, these would need to be of odd parity. For instance, if you make a diffeomorphism on the metric, you will generate terms like, well, I don't know if that can be seen in the other room, xi comma j plus xi j comma I, lead derivative of the metric to leading order, and of the flat metric even, okay? And you can see that if this has to be even, because that would be a term of 1 over r, if xi is of order 1, this would be 1 over r, but it has to be even. And for this to be even, it can differ by a constant only by odd parity terms, because you are taking different derivatives. So these transformations should be of definite odd parity. However, you can show that these extra transformations, now, okay, not only do they leave the boundary conditions invariant, they also leave the action invariant. So they can be called symmetries because the action is invariant. And so you can write the generator, and you will find that the generator in that case is pure bulk, only the constraint. So they have 0 charges. And so even though we have this infinite dimensional set of extra generators, because they have vanishing charges, they are proper, you can factor them out. So the true asymptotic symmetry will just be the Poincaré group. And so this was a result somehow in conflict with the asymptotic analysis at null infinity, where the asymptotic symmetry was found to be much bigger. So there was a tension, and that tension, it was realized, is due to the fact that the boundary conditions that I wrote involve an improper gauge fixing. And so this improper gauge fixing freezes the non-trivial BMS supertranslations, and because they freeze the non-trivial BMS supertranslations, you don't see them. Okay, you are just making a gauge fixing which is too strong. You see, it's like if I was imposing coordinate conditions where things would always be addressed, I would not see that it's possible to boost things. So here you are making you are imposing conditions that forbid you to make the non-trivial BMS super translations. And one can immediately see that this is the case because in fact, the standard BMS super translations, if you go back to that slide, they have the opposite parity. They take the same form. I mean, they are a function of the angle, but they would be of even parity, these two. And so because of that, you are actually freezing them when you impose these boundary conditions. And so the idea, which is relatively direct, is to unfreeze that. So how can we unfreeze that? Well, we take parity conditions which are less strong. We still need parity conditions, otherwise the formalism is not consistent in the sense that the action would not be finite and you would not have canonical generators. But the idea is to allow in the asymptotic form of the field, besides this strict parity invariant or even or odd terms that I wrote, to allow for a term which is just the result of making a non-trivial BMS super translation. So we call that a parity twisted component. So let me explain. So I would take two leading, so these are the leading orders that I'm writing. So I would take the same parity even or odd leading order as in the Regge-Teitelbaum approach, but I will allow an extra term which represents in Hamiltonian form a transformation under diffeomorphism. Now they will be of the same order, 1 over r and 1 over r squared here, but they would have the opposite parity. And so that's why we call that parity twisted conditions, but twisted by a diffeomorphism. Now you can show, and I will not go through the technical details. I mean, this is in the references that I can give you if you are interested, that if you really want to preserve the boundary conditions, if you want to have a finite action, if you want to also have a theory which is asymptotically invariant under Lorentz boost, so you have which are always tricky to handle because they explode at infinity. So I mean, to have finite surface generators is more tricky with the Lorentz boost, also for angular momentum. If you want to have all this well defined, you have to actually not consider arbitrary diffeomorphism in this asymptotic form, but it turns out that in the end, when you do the analysis, the diffeomorphisms that you can allow here are parametrized by Uij by one single odd function of the angle, while the other one, Vij, is parametrized by a single even function of the angle. So there are some extra conditions that you have to impose. Well, actually, you can show that the opposite parity is in fact pure gauge, it's proper. So the parity is not really a restriction, but the fact that there is a single function parametrizing the spatial diffeomorphism is perhaps not so obvious, but it comes out from the formalism. So let me skip the technical details. And believe me on that, but it's in the references, so it's documented. Now, you might ask the question, do these relaxed parity conditions involving that extra twist lead to a consistent description? Well, you might say a priori, well, trivially it must be so, because after all, I realized that my boundary conditions did not allow me to make BMS transformations. I will just see what is the action of a BMS transformation of my boundary conditions and allow such a term. And since, after all, the theory is diffeomorphism invariant, everything should go through. Well, the theory is really diffeomorphism invariant up to surface terms. And if I want the surface terms to be tamed and under control and if I want my action to be invariant and that the surface terms that will appear are not infinite, I mean, all these things have to be checked because I'm making improper gauge transformations. And so for which I know that things are invariant up to surface term, but these surface terms might be divergent, might be whatever. So it's not this check is not completely trivial. That the boundary conditions will be automatically invariant under BMS is trivial because they are built to be so, but that the formalism allows me to consider such relaxed parity conditions is not completely trivial. So in particular, do I still have a finite symplectic form if I allow this more general form of the canonical field? Do I have well-defined generators? This is to be examined. Now, this has been examined, and the answer is affirmative. So these boundary conditions that I wrote, after some work, can be shown to be consistent. So the idea is elementary in a sense. I think one could have thought about that much earlier, but and there is some technicality that has to be checked. And so in the end, you find that the BMS, that the theory, the formalism is invariant under hypersurface deformations that behave asymptotically in this way. So let me again have the whole text. So where you have some blowing up terms at infinity, then you have order 1 terms. I mean, these are functions only on the depending on the angles. This function is parameterized by a single function. That's what I told you, that there is a single function parameterizing the allowed order 1 diffeomorphism. Now, this one parameterizes the diffeomorphism along the normal, so off the surfaces. This one is tangential to the surfaces, but it has to take that special form. And so that one is even and that one is odd. Well, in fact, the odd part of T would be pure gauge and the even part of W would be pure gauge as well. Now, these terms are familiar because they just describe the Lorentz boost. I mean, the Lorentz boost, this one. I mean, you are tilting the hyperplane by something that blows up at infinity linearly. And then this one describes spatial rotations, okay? So, which also blow up at infinity. Then the next term, well, the zero mode of T, which is even, corresponds to just ordinary space-time, time translation, sorry. And the first spherical harmonic of W, which is odd, the first spherical harmonic, through that formula will define you a vector field, which is actually just the ordinary translations. So part of T and part of W describe the known space-time translations, but there is more to it. The higher spherical harmonics describe general supertranslations. And in fact, you can show that the even function T and the odd function W, if you want to compare with null infinity, they can be combined. I mean, it's not just the sum, it's slightly more complicated, but they can be combined to form a single arbitrary function of the angle, as in the null infinity description of the supertranslations. Yes? Okay. I don't know where to look. Ah, there. Okay. Yeah, I can see you. I see you from the side. Well, these, yeah, okay, so that will be in the next slide. I mean, you can completely relate them to the charges that people find at null infinity. And so in particular, all this infinite set of word identities are really word identities corresponding to these charges and additional symmetries. Because a connection can be made. I will say slightly, I mean, I will say more in the next slide. So if you are unhappy with what you see, please come back with a question, okay? Okay. So now, so first of all, these, okay, so let me continue and say a little bit more on the question when I'm on the next slide. So if you can compute the symmetries associated with these transformations using the, I mean, after all, they are canonical transformations, so they have the generator, sorry, so you can compute the generators, which I have written here. So it's a combination of the constraint plus some surface term, which is finite. And the explicit form can be found in the references that I have not given to you, but which I can if you are interested. Now, you can also compute the algebra of the generators. You have a Poisson bracket structure. It's their canonical transformation. You can compute the Poisson bracket on the nose without having to regularize. Everything has been tailored so that things are finite. And the algebra of the generators is actually the BMS algebra. So in particular, the super translations transform in the Lorentz representation appropriate, for super translations. So it seems that we do have the BMS group at spatial infinity, and indeed, you can match things with the null infinity results. And so in particular, the matching conditions of Strominger, which involve this the antipodal map, but between future null infinity, the past of limit of future null infinity and the future limit of past null infinity, are a consequence of the boundary condition at spatial infinity that I have given. In other words, if you evolve initial data that fulfill these boundary conditions at spatial infinity, you will get a geometry, a field, a gravitational field, which fulfill exactly these matching conditions. And it's not completely surprising, because in order to go to null infinity, in a sense, you have to boost infinitely the space-like hypersurfaces, but then this antipodal map will relate the past of future null infinity with the future of past null infinity. As in the limit, they will touch these critical surfaces. And so that there is a connection between the two is not a surprise, but you can explicitly prove it, that the fields obtained by integrating initial data satisfying this will fulfill the Strominger matching conditions, and that the BMS symmetry, the transformations, if you look at how they act at null infinity, or to be more precise, this infinite dimensional group obtained at spatial infinity, if you look at how it acts by integrating to leading order the equations, if you look at how it acts at null infinity, you will find that these are just the BMS generators that people found at null infinity. And so from that point of view, there is a complete match between the two. And also we see that we do get agreement only because we have allowed these relaxed boundary conditions in which we do not impose strict parity conditions, but in which we allow for this twisting by a BMS, now we can say BMS, by a BMS transformation. And the problem that was encountered before was that somehow there was a gauge fixing of the BMS group, which is something you cannot do because it has some physical consequence. There are non-trivial word identities associated with it because they are non-trivial generators. Now, I should say that in particular, well, I mentioned that briefly, and this is perhaps more for the people who know these mathematical developments. The parity conditions that I have given here, so which are strict parity conditions, even for the leading order of the metric, odd for the leading order of the conjugate momentum, up to a gauge transformation. So they are twisted by a gauge transformation, by a diffeomorphism. They define initial data, and that's why we can do the matching easily, that do not lead to these log singularities that I mentioned earlier. So I told you that if you take initial data which would otherwise be reasonable, so suppose you don't impose a parity condition, you might say, why should I impose them? Well, you will find that the opposite parity component, so odd for the metric, even for the momenta, if they are not obtained by a diffeomorphism, so if they take a more general form, they will lead to logarithmic singularities as you go to null infinity, even in the Weil tensor. And so the taking limits as you go to the critical surfaces corresponding to the past of future null infinity and the future null infinity with more general boundary conditions would seem to be problematical. And I think it's quite interesting to point out that these twisted parity conditions that I presented you, they were introduced in order to make the Hamiltonian formalism satisfactory. I wanted to have a finite action. I wanted to have a canonical action of the Lorentz boost. I did not give the details, but I told you that this was the way we arrived at this form of the boundary conditions. And as a bonus, we get that there is no singularity, or at least that we get a smoother null infinity than arbitrary initial data would lead to. But that is not the way they have been constructed. So in a sense, it's a non-anticipated bonus. Now, I should say, however, that if you just look at the canonical formalisms, there are other ways to fulfill these consistency conditions. Other parity conditions can be given. I mean, they are not related to Ray-J-Teitelbaum parity conditions in the way I have described, but some different twists can be given. And from the point of view of the Hamiltonian formalisms, are perfectly satisfactory. If you integrate, however, to null infinity, they would introduce logarithmic leading behavior in the Weil tensor, for instance. And now, I'm not sure that this is bad or not bad, okay? Because from the point of view of the Hamiltonian formalism, Cauchy surfaces, spatial infinity, they are good. It's just that they lead to a more complicated null infinity than what would have liked. Okay, this being said, let me go over 5 dimensions. And 5 dimensions you treat exactly in the same way at spatial infinity. Conceptually, at least. The difficulty is that non-linearities of gravity show up in the asymptotic expansion in a more complicated way, and so there will be new or more complicated technical features, but conceptually, it's really exactly the same. So it's good to understand the 4-dimensional case first, where things can be managed relatively easily, and then you can go to 5 dimensions, and then you have to be a little bit braver concerning computations, but conceptually it's the same. This is just what I said. So what is the idea? Well, you should include explicitly improper gauge symmetries, improper diffeomorphism in the asymptotic form of the fields. Now, it turns out, however, that the relevant improper gauge terms that you have to include are not anymore of the same order as the Coulomb part. Well, they are actually, so in 4 dimensions, both this extra term that I introduced and the strict parity invariant terms of Ray-J and Teitelbaum were both for the metric 1 over r, and for the momenta 1 over r squared. Now here we will see that the improper gauge transformation term will dominate in the 1 over r expansion the so-called Coulomb type part. Okay? And there will be no parity conditions, however, in 5 space-time dimensions. It's not necessary to make the formalism well behaved. So to be more precise, the improper gauge terms for the metric will be of order 1 over r, while, as we have seen by looking at gravity in higher dimensions, the rest, so the Coulomb type part at spatial infinity would decay as 1 over r squared. It's weaker at large distances, so converge Rothschild in 5 dimensions. But here you would have to keep improper gauge terms, so terms of order 1 over r, but restricted to take the form of gauge transformation of diffeomorphisms expressed in the Hamiltonian terms. So schematically, you would have that the metric will differ from the flat metric in Cartesian coordinates by a term which has a form of a diffeomorphism plus, well, let's say the core, which corresponds to what I call the Coulomb part or the Schwarzschild part or whatever, so which is of order 1 over r squared. So they are of different orders. So it's not parity conditions that make the distinction, it's the order in 1 over r. And similarly for the momenta, you would have an expansion of the momenta as something which has a form of a diffeomorphism, which is 1 over r squared, and then the core, I mean the standard Coulomb type part, for instance, or Kerr for that matter, because for Schwarzschild, pi ij is 0, so you have to have a rotating black hole to have a pi ij, so this would go like 1 over r cubed at most. Okay, so there is again a difference in the 1 over r expansion, okay, as for the metric. And then you just crank the machine. So the ideas are identical, technically more complicated, but you find new features. Okay, so the conceptual ideas, the starting point are the same, but then when you do the analysis, you end up with new features. First of all, the BMS5 group is bigger than what you should have, well, what you might have perhaps expected. I'm not sure which intuition one has, but you find that you have 4 functions of the angles instead of 1. that namely you can show that not only the leading term in the supertranslations will contribute to the charges, but the subleading term will also contribute to the charges. And yeah, and so they are non-trivial. I mean, they will be non-zero contributions. Then you find that some of the supertranslation charges, including the energy, acquire nonlinear contributions, even in standard coordinates, okay? But then, and because of that, you find that the asymptotic symmetry generators, when you compute the algebra of the Poisson bracket, they form a nonlinear algebra. You get a polynomial expression in terms of the charges themselves. And furthermore, there are also central charges among the different types of supertranslation generators, the one corresponding to the leading piece and the one corresponding to the subleading piece. So this is in that, actually, I'm giving a reference. So it's in these references which have been published since then. Okay. Now, maybe I will make two comments. Some comments on the nonlinearities in the algebra, and then comments on nonlinearities in the charges, just to, and then I think I should close. So I should say that the fact that symmetry generators, when you compute the Poisson algebra, the Poisson bracket algebra, form a nonlinear algebra is really the general rule, and it's a linear algebra, which is really the exception. I mean, it might be an exception that comes for very good reasons, but in general, you should not expect the symmetry charges to form a linear algebra. They will form a nonlinear algebra. And this is perfectly okay. It just means that the canonical transformation generated by the charges, when you compute the commutator, it will take the same form, but with coefficients that will be functions of the fields, but of a very particular type. They will depend on the fields only through the charges. So it's okay. You know, we know very well that if I have the free particle, the momentum p is conserved, but then p squared is conserved, pq is conserved, p4 is conserved, any function of p is conserved. And when I compute the bracket of symmetry generator, I could get p cubed, for instance. Okay, it's not in the case of the free particle, but I'm just telling you that the charges are not, in general, expected to form a vector space. I mean, you have to look as to whether they are functionally dependent or independent. Now, there is a great flexibility in the presentation of nonlinear algebra, since you can make nonlinear redefinition of the charges. In fact, the charge is defined a Poisson manifold. In the finite dimensional case, it's well under control. There are classification theorems of Poisson manifolds, which generalize the Darboux canonical form. So when the Poisson bracket is non-degenerate, we all know that that there is only one Poisson bracket structure locally, I mean, which takes a canonical form in Darboux canonical coordinate. When the Poisson structure is degenerate, it's more complicated, but that has been done by Weinstein. So it's a Weinstein splitting theorem that gives you some classification, and sometimes people call it Darboux-Weinstein theorem, since it generalizes Darboux. Now, in the infinite dimensional case, which is the case considered here, I think that the situation is much less understood, so you have to work more as a pedestrian. But we have done some simplification of the algebra, and we could bring it to a form in which all the nonlinearities in the Poincaré subalgebra have been absorbed. So the Poincaré, the Poisson brackets of the generator of boost, spatial rotations, and translations are all the standard ones. So for Lorentz, perhaps it's not so surprising because it's some simple algebra, and there are some theorems that show that it's difficult to non-trivially extend such algebras, but we have also the translation, so it's slightly more subtle. But okay, they are not. We can eliminate them through the redefinitions in such a way that the nonlinearities only occur in the brackets of the boost with some of the proper supertranslations, and the supertranslations themselves form an abelian algebra with central extension. Now, as I said, there is also a there are nonlinear terms in the supertranslation generators, in particular in the energy, which does not take the familiar ADM expression in for D. With our relaxed boundary conditions, it acquires nonlinear contributions, which I have written here. So let me just flash the ideas. So in the expansion of the metric, the first term here, that's 1 over r squared, so this corresponds to the Coulomb piece. That's 1 over r, but I'm in polar coordinates, so these are angles, capital A. So this would also correspond to the Coulomb piece. And in GAB, so the angular component, so this is what the value for flat space, and this would correspond to the Coulomb piece, which is 1 over r squared lower than the leading piece. But we have an intermediate part which is due to this extra diffeomorphism contribution that I explained, which we have called theta AB. So I'm only saying this to say that it contributes to the energy. It turns out that this term contributes to the energy in the following way. K, you don't need to know what it is because it's irrelevant for what I want to illustrate. It comes from the momenta, but it's not needed. Now, this would be the ADM, linear ADM expression related to the Coulomb part, the decaying, to the part decaying like the Coulomb field at infinity. Okay, and this is what is due to the extra term that I have included, which decays slowly here. Okay, and you find that just by cranking Hamiltonian methods. You have a canonical transformation, find the generator, it will know how to do. Now, the nonlinear terms are crucial for understanding some puzzles that was pointed out by Crucial some time ago. So and he observed that if you take the ADM form of the energy and allow coordinate transformation that decay slowly at infinity, then and do not preserve the 1 over r squared behavior of the metric, but induce a 1 over r term, as I showed, then the ADM expression for the energy is not invariant. And that is very well explained in his lecture notes. It does all dimensions, but if you take 5 dimensions, you have to put, there is a parameter alpha that you have to put it equal to 1. And so if you in particular make a coordinate transformation of this type, so it's not a standard translation, you are just shifting the radial coordinate, but by something that differs from the radial coordinate by a term 1 over r. So I could write this rho parenthesis 1 plus c over rho. So this term is 1 over rho smaller than the leading term. Okay, so I make such a coordinate transformation and substitute that in the metric and compute the ADM energy after I have made this spatial coordinate transformation. So it's not that I'm boosting or doing whatever. I'm not changing the slice. I'm just changing the coordinates. I'm doing that. And then you observe that the new form of the ADM energy is not, and even you do that in Minkowski space, is not equal to 0. Okay? Well, actually, the puzzle is resolved because the ADM expression for the energy, which was devised for 4 dimensions under some boundary conditions, is not the valid expression for the energy. They are extra nonlinear contributions. And if you include the nonlinear contributions that come from this theta AB that I explained, it turns out that it is transformed under this coordinate transformation. You find that the energy remains invariant. So it's crucial to introduce, if you allow these more general transformations, it's crucial to have the correct expression for the energy to make sure that it is invariant. So I think I am over time, so probably I should conclude quickly. Okay. Okay, but I don't want to abuse, and probably there are hungry people in the audience. So let me just say one slide on higher dimensions and then conclude. So as you increase the dimension, go to 6 dimensions, 7, 8. Well, the analysis conceptually, although I should say that we have not done it explicitly because it becomes more intricate and much more intricate. You see we have nonlinear terms appearing which were quadratic. As you increase the dimension, you will get things will be more complicated. And why will they become more complicated? Because the gap between the pure improper diffeomorphism P that you have to include, which will always be 1 over r, and the Coulomb part, as we have seen, will widen as you increase the dimension. You see, in 5 dimensions, we had the metric goes as 1 over r squared for Schwarzschild. In 6 dimensions, there will be 1 over r cubed. but we have to include a diffeomorphism part that starts as 1 over r. So there will also be a piece in 1 over r squared that generated by the diffeomorphism, and then there is a 1 over r cubed term. So you see that we have, in the expansion, more and more terms that we have to keep. And this increases difficulties because there are more and more non-linearities that become relevant at infinity. And they proliferate, in fact. Now, even though they proliferate, it seems that, okay, and in fact, they are not seen in most treatments of null infinity because people linearize the theory at infinity precisely because of these complications. Now, it seems that the size of the BMS group will not increase with respect to 5, well, or it will increase just in the standard way because the new terms that you have that will appear actually would define proper gauge transformation. But this is just what we have guessed. It's not proved. So maybe this you should not read. Okay, but so let me just in a sentence, 6 dimensions and higher. It's in principle doable, but it's much more complicated, and we have not done it, although we expect no real surprise. It's just there will be more non-linearities. So the conclusion of my talk is that in order to see the BMS group at spatial infinity, and we have every reason to believe that the BMS group has some physical, non-trivial content. I mean, especially because of, as we know, there are word identities associated with it. Okay, so if it has some non-physical content, it should also be seen at spatial infinity. And we have seen that in order to see it at spatial infinity, you should make sure that your boundary conditions are not killing the possibility of making BMS transformations. Because if you are making too restrictive boundary conditions, adopting too restrictive boundary conditions, it's clear you are not going to see the BMS group. Okay, but if you do choose the more relaxed boundary conditions that allow the action of the BMS group, you do see it. You do see it not only because it preserves the boundary conditions, but also because consistently it can be incorporated in the Hamiltonian formalism. And as I said, this is satisfactory because we know that we cannot gauge fix improper gauge transformations. We can only gauge fix proper gauge transformations. Okay? Now, in 4 dimensions, we are fortunate that there is, and that was done before, the null infinity treatment, and we can compare, and we find that the boundary conditions are in complete agreement with null infinity. And actually, we can also show, for instance, that we can derive the matching conditions that have been used in null infinity analysis from the point of view of initial data. So we can justify these matching conditions in the sense that we have initial data which are such that when I integrate the equations of motion and see what I get for null infinity, and really I think null infinity is a dynamical question, I do get matching conditions that have been considered in the literature. Now, that's also true in 5 dimensions, that we can satisfactorily construct a non-trivial infinite dimensional symmetry group. Of course, to compare with null infinity is more difficult because I have not seen a 5-dimensional null infinity description. In general, null infinity is easier in even space-time dimensions, and so that's most of where the analyses have been carried out. And these 5-dimensional results are quite, I think, interesting because of the asymptotic symmetry algebra is nonlinear. We have more super translations also, but especially we have this nonlinear realization, which is not the first instance that we do get nonlinear realizations. We have seen that higher spin gravity in 3 dimensions, for instance, also involve nonlinear W algebras, but there it's more under control because representation theories of W algebras is under much better control than the representation theory of these nonlinear algebras that we get in 5 dimensions at spatial infinity for asymptotically flat space-time. But I think that it would be quite interesting to derive the implications of that symmetry, which has not been done so far, in particular in terms of the physically relevant representations of this BMS5 symmetry. But this is, as I said, is work to be done. And with that, I will thank you for your attention.